Hello everyone, and today we are going to discuss the part 4 of groundwater exploration. If you recall in the previous discussion where we left with this slide is about finding out a ratio between benefited area versus submerged area. Because for all kinds of analysis, you cannot have all the time qualitative analysis. So, one has to find out some ways for doing quantitative analysis which are better to convince the audience or decision makers. And this kind of analysis or ratio has been developed which is between benefited to submerged area ratio. So, what basically if we consider as a in this schematic, if we consider it is a watershed, then and then there is a dam or a reservoir or dam access is there, then this is the darker grey area is the inundated area, whereas through growth of vegetation in the downstream of a reservoir, we can delineate the benefit area, and this technique can be used successfully in case of hard rock terrain. And in previous discussion, I have shown many examples from that is hard rock terrain like Bundelkhand Craton or in Deccan Trap and other places. Using satellite images or even Google Earth images of almost 2 color images, one can identify these 3 things together. One is where is the reservoir, upstream area, that is the submerged area, another one is the benefited area. And if we create if we find out the areas of these 2 submerged and benefit, then benefited versus submerged ratio can indicate lot of things. That if the ratio is more than 1, then that means that it is causing a positive impact in terms of a growth of vegetation or groundwater recharge indirectly. So, in case of I am showing an example from that Bundelkhand granite, and what I am showing the examples here, there are about 25 or 28 reservoirs which you are seeing here. So, based on satellite images, a benefited area has been identified for each reservoir which are given here on the first column. Then submerged area was also estimated using satellite images, and easily then a ratio was developed. Now, here what you observed that if I take the first reservoir, which is the Chanderi reservoir, here this benefit versus submerged area ratio is 28.18. That means very clear indication is that in the vicinity of this reservoir or in the same area where the setup geological or topographic geomorphological setup is almost same, then if I construct another groundwater recharge structure, then 28 times benefit I am going to have or 28 times return I am going to have, because in that case I will be submerging only 1 square kilometer area for example, and in return 28 square kilometer area in the downstream will get the benefit of groundwater recharge, and indirectly we can assess through the growth of vegetation. So, this kind of ratio development of ratio for any hard rock terrain is very useful to citing the future reservoirs or future groundwater structures in the vicinity of that one. If I take the another example which is the extreme example at the bottom, which is a Jamalpur reservoir, here this benefit versus submerged ratio is 0.6. So, this is not the area to develop for groundwater recharge structure. What 0.66 means is that if I submerge 1 square kilometer of the area, in the downstream I am going to have benefits only in the 0.6 square kilometer of area. And that is not a good ratio, and that is not a place where future investment in terms of groundwater recharge structure should be done. However, if we decide or decision makers decide in the field, because yesterday or in the previous discussion I told that there are some states which are doing lot of extensive work towards groundwater recharge, and they are creating groundwater recharge structure. So, before they decide the location of such reservoirs or groundwater recharge structures, the best thing is they should first assess for the entire area this ratio of existing reservoirs. And if they too find that some reservoirs are giving a ratio value is 30, then or 25, even up to 10 say, that is still good. So, it should not be less than 1 like in last case in Jamalpur, otherwise even the second last one is providing about 3 times return. So, no harm if land is available, and if since water is available, then still we can create the structures. But say initially we marked a line that below 10 we will not take any new structures in those areas. Fine. So, at least these are the areas in the vicinity of these reservoirs, these are the areas available where we know for sure that if a 1 square kilometer of land is invested towards the reservoir submergence, then I am going to have 10 times return from this. This is very good to assess or forecast what is going to happen in future in those areas. And we can convince the decision makers that if you construct a groundwater recharge structure or reservoir in such areas, I can assure you that you would get 10 times return in terms of groundwater recharge in a downstream area and ultimately growth of vegetation. So, that kind of forecast is possible based on the knowledge which we develop through this studies of satellite images and demarcating submerged area versus a benefit area, and by this ratio we can assess. So, this gives a very good indication about what would happen to a structure, how much benefit, because this is a very straightforward question which is raised by the decision makers whenever we suggest for some groundwater recharge structures. The first question is how much area will be benefited. So, if already in that area some small, large, whatever reservoirs are existing or groundwater recharge structures, if we do this simple analysis, then we can tell. So, if I am working in this area where I myself has created a ratio value is 10 and above, then I would assure them that at least you are going to have 10 times return. No bank, nobody will give you 10 times return, but this land can give you 10 times return. This is a wonderful investment if it is done in these areas. Of course, the investment should not be done in the last case, which is Jamalpur reservoir, but otherwise we can convince the decision makers that this is how the return will come. The second question they will ask that how much time it would take to get returns, or how much time it would take that groundwater regime will get recharged and the benefits will start coming in terms of growth of vegetation or agriculture crops. That answer too we can answer, which I will be just discussing with this. Here we can answer that how much time it would take, and this is a time series data of 2001, 2002, 2003, 2004. A reservoir, a large multi-purpose reservoir was coming, which is also called Rani Lakshmi Bai reservoir or Rajghat reservoir again in the Bundelkhand region. These are the MODIS images freely available. Of course, resolution is 250 meter spatial resolution, does not matter. Our purpose is different, we wanted to cover a large area. So, this kind of resolution is even do our purpose. So, what you see in the first one, that a reservoir was about to filled, in 2001 it was about to complete, and next year you can see the water has come. These are the true color images. So, vegetation will appear in green. So, what you are seeing in 2002, some water has already come here, and also keep watching in these 4 images in the time series growth of vegetation. Now, this is 2003, and you see in the downstream area where earlier there were hardly any vegetation in 2001, now it is showing the growth of vegetation. And just see when this whole reservoir or project was completed, it is a multi-purpose dam, and it is hydropower, it is having irrigation through canal and lift irrigation also. So, the water is also going across this watershed or boundary, which is between 2 states, Madhya Pradesh and Uttar Pradesh. But does not matter, this huge water body which was created, which has submerged some part of land, you can assess that how big area has already got benefited in just 3 years time. So, in these areas you can say, like based on this ratio analysis, benefit versus submerged analysis, you can say that at least if I make a threshold value that 10 or above I will consider, then immediately you can tell that 10 times return will come and these returns will come in minimum 3 years time. Then the decision makers will get very easily convinced that yes, these are the areas where such investment towards the groundwater recharge structure should be done. One more important thing I can share with this, that the indirect evidence of what kind of benefits the farmers got. The greenery which you are seeing is not the entire development of forest, but this is the agricultural land. And in 2004 started in 2003, 2004 and onward, so much grain production was there in this area that the local mandis could not handle that one, or local wholesalers could not purchase from farmers because they did not left money to purchase farmers. So, from outside area, means from other places of India, people came and purchased the grains from this area, because suddenly in 2 years time the production increased by many folds from this area. So, because the soil was available, the only problem, the farmers were there, human resources were there, only problem was water. And once the water became available, even in tube wells, even in wells, they could grow the crops. Similarly, in the same area, when the crops started growing, a lot of these pumps to withdraw water from open wells or dug wells or tube wells were purchased in this area. And similarly, large number of tractors have also been purchased, large number of motorcycles have also been purchased by the farmers who got benefit immediately once this reservoir started getting filling. So, you can convince people that you will get this much of benefit, you will get benefit after 2 years or 3 years after the construction of. But this reservoir is a multi-purpose reservoir. It took the gestation period, the construction period took 30 years. There were a lot of environmental issues and other things. So, I am not suggesting by any way that we should go for large reservoir, multi-purpose reservoir. What I am saying that in this area, wherever we see that there is no growth of vegetation, however rainfall in this area is around 950 millimeter annual rainfall. So, it is not insufficient rainfall because it is a hard rock terrain. So, the surface runoff is very high. So, by creating such recharge structures, we can delay the surface runoff, we can store water on surface for some time, that will recharge the unconfined aquifer conditions and you get the water very quickly. So, this kind of a simple analysis based on remote sensing at the very early stages of groundwater exploration can really help, and can help also to take appropriate or nice decision for the development of an area and benefits for the farmer. When if you see these images, one might feel that probably I am showing the images pre-monsoon and post-monsoon. So, for 2001 I am showing image of pre-monsoon, for 2004 I am showing image of post-monsoon. No, it is not correct. The same date images are there. Now, I will show you further. See the 2002 when the reservoir started filling, you see the growth of vegetation. There is the same date for all these years, 17th December 2002, 2004, 2005 and 2013, and see that entire area after roughly 8-9 years became green, completely green, and you can see how the agriculture started doing much better and better and better, just because of one major reservoir which came in this area. Again I am repeating, I am not suggesting for groundwater recharge any major reservoirs. Even small reservoirs can also provide good benefit area, as we have discussed in early discussions also in part 2 or part 3. So, this kind of analysis using satellite images can really help, can really convince the decision makers to take right decision for a particular area. Now, if you see that 1984, I am showing two images, 1984 and 2021 from the, of course, these are two different satellites, but the area wise it is same, georeference in the same manner. So, what do you see that, see this river, both are December images, and see the greenery in the December 2021 compared to what was in 1984. There were no reservoir, there were no checking of water, the entire rainwater was going as a surface runoff. Only minute quantity of water was going in the subsurface conditions through the infiltration and percolation. But because of reservoirs, see the downstream area completely changed and greenery has come, farmers are happy, a lot of they are growing now not one crop, but they are growing 3 or 4 crops per year because of availability of water in their wells, because of the recharge which is being induced by this reservoir. Hydraulic gradient is also good because this reservoir is having quite good height. So, it provides a good hydraulic gradient, good groundwater recharge. Farmers are having water available in their field, they have to just pump out and put in the agriculture fields. There is of course some canal irrigation system is also there. That too, because all the canal irrigation system in this area are all unlined. So, they too are recharging the groundwater regime. One more image I will be showing of 1990 and 2002. You see, even in the monsoon time, this was the situation in 1990, but in monsoon time in 2002, see this area, downstream area. Hardly any vegetation in 1990, we did not have the reservoir, only started coming in 2001 and now you see in 2002. So, this kind of benefits can come, and this is the joy of water in a hard rock terrain. Earlier there were no water, now this is the unlined canal originating from that reservoir which we have been discussing, Rajghat reservoir or Rani Lakshmibai reservoir, and wherever this canal is going which is unlined, it is recharging groundwater regime, and people in their front of their house are having a water body, flowing water body, fresh water body. So, not only the humans are enjoying, but animals too are having benefits of that, and of course, you are having growth of a healthy vegetation in the surroundings. With a very basic analysis employing remote sensing data, one can achieve such kind of results for, especially for I am talking about hard rock terrain. These are the areas which are having real challenges about groundwater, not only Bundelkhand, but other hard rock terrains area, including the Deccan Trap areas or this basaltic terrain of Maharashtra, Madhya Pradesh and Gujarat also. So, that kind of benefits can be assessed before anything happens on the ground, and that is the advantage. That is real modeling, I tell you. This is real modeling, a very simple modeling based on satellite data which are providing synoptic view, which is a completely unbiased recording of the things, and data is available free of cost. Most of the data which I am showing here is all available free of cost. Just download and do the analysis and suggest to the decision makers or forecast to decision makers. Give this forecast, give this production to the decision makers. This is how you can recharge the groundwater regime. This much area will get benefit and this much time it will take to see the benefits on the ground. Now, I am going to show the reservoir which I was discussing is here. This is the Betwa river which is moving like this. This is another dam which is a little older dam, Matatila dam, and there are one more dam is coming here. There are so cascading dams are there, series of dams on the same river. So, whatever the water which is going as waste in monsoon time is being tried to capture and store on surface water body. Later on it recharges the groundwater regime. So, anyway, this is a total area of this Bundelkhand Craton which is having exposed Bundelkhand granite or gneisses are here. This total area is 29,000 square kilometer, and this area is really having acute scarcity of water. Earlier it had more, now it is reducing because of these successive reservoirs and efforts are being made, and that is why. But still there are areas which you can delineate very easily in the satellite images that efforts are now required in these areas, so that the entire Bundelkhand Craton becomes green in a true color image which is available on net or MODIS image or Landsat image or IRS image, does not matter. So, that these are the areas should be targeted now. There are small reservoirs are there which should be studied, and then ratio should be found out, and based on that ratio you can forecast to the decision makers that this is what is going to happen. We did some further analysis on this which I will try to convince you further on this. Now, where exactly reservoirs should come and how to exploit these quartz reefs which I have discussed in earlier discussion, because if you see these this image, there are hundreds of quartz reefs running northeast southwest, and on the ground this is how they looks on the ground. So, if we identify an area like on the satellite image here, which I am showing the image here, if we identify a quartz reef which is being breached by a stream like here, then this is the best place to construct a recharge structure or a small reservoir or a dam, because we can exploit these quartz reefs. These quartz reefs will serve as a dam access. As you can see on the ground, this is how they looks, and it is about 25 to 30 meter higher than normal ground. So, this 30-meter dam access is already made by the nature, which is available to us. Our ancestors knew about this. At places they have exploited this quartz reef as a dam access to create a reservoir. So, why not today? We can identify each and every stream which is breaching these quartz reefs, just check that stream. And most important thing is, you need not to, for the checking or creating a dam, you need not to go for too much engineering structures. You can use the local material available here and there and put that in one and check the flow of water or surface runoff or a stream, so that it holds water for some time. The surface runoff delays for some time, and if it is there, because this is unconfined recharge, unconfined aquifer conditions, definitely in few months time it will recharge the groundwater regime and the benefits will start coming. So, it is a very simple solutions, at least for this area, to exploit already existing hundreds of quartz reefs which are running northeast to southwest. Our normal flow direction or slope direction is towards just opposite of these. So, they perpendicularly most of these streams are cutting, and that is the place where reservoir can be constructed as shown here, that this is the quartz reef which you are seeing. This is so this we can use as a dam access, and even the depth of dam may not be, the water column may not be very good, but still it is providing 25 to 30 meter. So, if a dam is created say up to 25 meter or 20 meter, it still it will hold lot of water. It will delay the runoff, and that will provide a direct benefit towards the groundwater, and in downstream area people will get benefit, farmers will get water in their wells and tube wells, and they can exploit that water for, instead of one crop they can go for 2 or 3 crops. That has already changed the scenario, but still there are areas which I have shown in the previous figure, that these areas should be now targeted to create a better groundwater recharge regime there. So, simple methodology is there. You can imply the Landsat data, you can imply the SRTM or digital elevation model, which I will show you why, and you can use these colored images, false color, true color, and you can map the quartz reefs with higher spatial resolution. When you are finally going to decide, do some field investigations, may imply some high resolution satellite images, of course survey of India topography, do the georeferencing for entire thing, create a land use map which will be used little later in further our analysis. A stream network can be also delineated from digital elevation models or from satellite image or from topo sheets. Stream network connections can be also found out, in identification and mapping of potential dam sites. That is the ultimate aim. That is the ultimate aim of doing all this analysis, to cite those areas where future groundwater recharge structures can come. And once you decide the site, then you can also find out how much returns it will give in terms of groundwater recharge or ultimately in terms of growth of vegetation, and second, how much time it would take. So, that estimation or that forecast can also be done. Further in future discussion, I will be showing how dam simulation can be employed here, and then finally you can make more appropriate, more accurate, more right decisions for such areas or for any hard rock terrain, the methodology which I am going to narrate here. Now, on the left top left you are having a satellite image, and you are seeing several large and small water bodies. So, there are 2 major large water bodies and rest of the areas are there, but there are certain streams may be smaller which has not been checked yet. If you see this reservoir, this is submerged area, this is the benefit area. But this reservoir is also providing a benefit area in upstream, similarly this one also, and this reservoir is also having benefit area in downstream as well. Our aim is to provide groundwater recharge. Now, groundwater recharge in this area, if it is going in the surroundings of the reservoir or even upstream, does not matter. My purpose is to delay the surface runoff, hold the water for some months, therefore, it will recharge the groundwater regime, and hence it will provide water in the farmer's well, and that water will be exploited for growing crops, different crops in different seasons. So, here satellite image is one of the inputs to delineate very clearly these potential dam axes. You can also employ digital elevation models, create a hillside or shaded relief model in GIS, and you can see that how these quartz reefs are appearing in this hillside. Drainage network from GIS surface hydrologic modeling can also be derived, and then you can see all this how you can drive drainage network, how you can create hillsides and other things have been extensively in detail have been discussed in the another course, which is Geographic Information Systems, which is a 60 lectures and 30 hours course. That can be referred, videos can be referred, or text can be referred to how to do all these things. So, I am not going in detail about those sections. Now, if you see this quartz reefs which I have been mentioning, these quartz reefs, they are which have been mapped in this area using moderate resolution satellite images, but for specific areas one should go for a higher spatial resolution images, does not matter. So, you see that most of these quartz reefs are running northeast to southwest direction. A rose diagram also clearly indicates that the orientation of these quartz reefs is northeast to southwest. But the important and beneficial point here is that the general slope direction, flow direction is from southeast to northwest. So, these quartz reefs at places are being breached by these drainage network. Further, at places these dam axes or these quartz reefs have been already utilized as dam axes by our ancestors, and there are at places where so far these have not been exploited. So, we can now, having knowledge, we can do it very quickly and can recharge the groundwater regime. See, these quartz reefs are spread all over the places, and like here in a high resolution image, it has been clearly identified. A dam has been for simulation, a dam has been proposed. So, length you know, and height we can decide based on the height of quartz reef, remnant quartz reef compared to the ground. So, if it is 20 meter, then this one may be of 200 meter length of the dam, and height of the dam can be say 25 meter. So, likewise. So, now dam location has been decided for simulation, and this is what is done. Now, employing again GIS and the course which I have just mentioned, in which this simulation part has also been discussed. So, here once the dam has been decided, dam axis has been decided, dam length has been decided, dam height has been decided, then how much area will get inundated, that can also be mapped based on the height which is being decided. Now, this is a simulation and it can be a iteration process also. What I mean by iteration process is that if you feel that there are some important areas which cannot be submerged, and therefore, in our simulation we can reduce the height of the dam. But if we feel that a lot of still a quite good part of quartz reefs as dam axes are available, we can increase the height of the dam in our simulation and larger submerged area can be mapped. So, this is being done through a modeling on the GIS platform. There is no issue, nothing is being done on the ground yet. We are just trying to assess the best possibilities which should be implemented on the ground later on. So, once you have decided say at this location with this length and this height, this is the submerged area. Similarly, in this topographic cross section, you would know that how to what reach the water will, what would be the wetted parameter and what would be the how the dam will look in the dam axis. So, this is the basically this is the area which has to be filled with the rocks or materials or RCC whatever, so that the dam becomes of this height. This is the inundated area, and of course, then benefit area, and this is how these quartz reefs sometimes looks on the field. So, you can see a stream is the same for the same area, the stream is flowing like this, the quartz reef it is just opposite of normal flow of general slopes, but in this local area it is flowing from northwest to southeast. Otherwise, general flow is from southeast to northwest, does not matter. We need to reduce the surface runoff, that is our aim, whatever the direction, does not matter. We can exploit these quartz reefs as dam axis, create as many as small check dams, small groundwater recharge structures, and recharge the groundwater regime in the area. Once that is done, then you can assess few more things. In the flow chart, I showed the land use. So, current land use which can be prepared using satellite images, when we overlay this part, immediately you would know that which land use will be submerged, whether some forest is coming, protected forest is coming, or some important monuments are coming. So, that therefore, you can reduce the height or increase the height of the dam during the simulation. Further, once you have decided, then you can bring below this submerged area, you can also bring this revenue records, the land records, and immediately you would know whose land, how much of his land will be submerged, and accordingly the compensation can also be given to the farmers or locals whose land is going to be submerged in this reservoir. So, the accurate analysis of even the compensation can also be done. Otherwise, generally these are very loose things, and the people then will go court and create litigations. But if we do this analysis, and if people if we go to court, we can convince the court that this much area, so somebody is having a location of his field is here, and he is still claiming that my area will be submerged, you can convince to the court that it is not true. My simulation very clearly tells that water of this reservoir will never reach to that place, because the height of dam is like this. I have simulated, I have modeled, and the water will never reach to that place. So, we did this land use analysis for this particular reservoir. You can see that different land uses in the future submerged area will be submerged. So, the decision makers can decide that what to do or what not to do. The major part in this particular example is agricultural land, which is going to be submerged, and then the other major part is, second most major part is barren land. So, barren land is good. So, only these much farmers have to be compensated. For barren land, that is government land, no compensation would be required. So, very easily all these analysis on a GIS platform, employing remote sensing, employing digital elevation model, and the concept which we are discussing here can give complete insight about a potential or future reservoir. How much area will get submerged, whose land will submerge, what kind of land use will get submerged, what will be the benefit area, and how much time it would take to get the benefits. All such analysis can be done before really anything happens, and this is what exactly is called modeling, spatial modeling. This is what is spatial modeling is. And this really is very useful in groundwater exploration at very early stages. So, I am showing few more examples of these kind of reservoirs. So, if you go in the field, these quartz reefs is a much zoomed slide. Quartz reef will look like this. It's a section, a road section is also seen. It's a really very hard mineral, and it is not going to deteriorate very quickly. And I am saying that even if we create a reservoir, some water goes in the downstream, some water remains in the upstream, does not matter. Ultimately, it is going to reduce my surface runoff, and that is the benefit. See, these quartz reefs are, if you going by road, many times you will encounter on the sites, these quartz reefs are running for hundreds of kilometers. Similarly, on the grounds further before construction of any such reservoirs, more geological or rock characteristics have to be studied, and this is what is done in that particular case also. There are a lot of such streams which can be exploited in this area, and a lot of examples of quartz reefs have been exploited in past to create such reservoirs. These examples are here. You can see the quartz reef has been used to create a dam. Similarly, a quartz reef has been used here to create a dam or water body or groundwater recharge structure, does not matter. So, quartz reefs can extensively exploited at places, and even if a stream is having say perennial stream and breaching several quartz reefs, we can have cascading such groundwater recharge structures at one quartz reef, then again in downstream another one, then another one. What is the problem? There should not be any problem, sufficient water rainfall is available, and if you delay the runoff, it is ultimately going to recharge. So, with the flag of a temple and a quartz reef, I end this discussion. Before I say thank you, it is important that as I have been repeatedly saying, simple techniques, free data and simple technology can be employed to do the modeling and convince the decision makers and create such structures in hard rock terrain. Example though I am showing from Bundelkhand Craton, but the similar kind of analysis in there may not be quartz reefs there, does not matter. Still these streams which are carrying water and wasting our surface runoff can be checked. Small cascading groundwater recharge structures on a stream can be created, and be sure, because in most of hard rock terrain, as discussed earlier, these are completely unconfined aquifer conditions. The water level is piezometric surface, and therefore, the recharging in the monsoon time is much easier of these groundwater setup or these unconfined aquifers. So, with this I thank you very much.